All right, good morning. Okay, so I got the final exam information pulled up here on the left screen. Same location as the previous exams, and just by looking at this, looks like the same seating blocks too. So, again, familiarize yourself with where you should go. A couple of these TAs have changed. For example, Doming Shea is now Jacob Bond, and Jeff Zielinski is now Christina Jamraz. So, but you know where you should go, even if the TA names have changed. There's the balcony too, as usual. All right, speaking of the final exam, let's look at the calendar here. Today we're going to cover section 16.9, and that's the last section we'll cover in the course. And the entire next week will be devoted to final exam review. Speaking of final exam review, I posted a set of practice problems on the course webpage. This is from a previous semester, but it looks pretty good, so I posted that set here. And it looks something like this. There are 54 of them. So, if you work through all of these and you know how to do all of them, you're in pretty good shape. Okay? Now, obviously, we're not going to be able to do all 54 in class next week. So we'll go through as many of these as we can. And for Monday, let's focus on the first 18 of them. Okay? For Monday, just go through the first 18 minimum. If you can go beyond 18, great. If not, at least look through the first 18. We'll focus on the first 18 for Monday, the next 18 for Wednesday, and then the last 18 for Friday. Sounds good? Yes? No? Good? All right. Okay. All right. Let's get my screens right. Okay, so the last section, like I said, we'll cover in the course is 16.9. Now we're going to look at another very useful and important theorem called the divergence theorem. So last time we saw Stokes' theorem that related a surface integral to a line integral. Divergence theorem, there's something very similar to that. What it does is that it relates a volume integral to a surface integral. So you see the pattern here. With Stokes, we related a surface integral to a line integral. So we related two things that differ by one dimension. Same thing going on here. We relate a volume integral to a surface integral. Again, these two things will differ by one dimension. We're always relating these two things. So here's what the divergence theorem looks like. The theorem says that the triple integral over some solid, we'll call that E, of the divergence of the vector field, dV, is equal to the surface integral of f dot ds. All right, so E is the solid, and S is the boundary surface of E. Okay? Sometimes you see this thing written this way. Instead of S here, some people will write this notation here. And we saw this thing last time when you have this little partial differential symbol with the E in this case. That means we're looking at the surface of whatever E happens to be. Last time we're looking at the boundary of whatever the surface happened to be. Okay, so this is relating the volume integral over the entire solid to the surface integral. So for example, the key thing here is to recognize what the surface, the boundary surface is. Let's say, make it very simple. Imagine that E is a cube. Then S, the boundary surface of that solid, are the 6 sides of that cube. Right, does that make sense? You look at a solid and you look at the boundary. If you have a sphere, then the boundary would be the surface of that sphere. Okay, as usual, a little bit of history lesson behind the divergence theorem. It's not named after a guy named Divergence. There might have been a guy named Divergence or a woman named Divergence, but it's not named after him or her. It doesn't get a scientist name here for some reason. But let's give some credit to whoever invented this thing. Today we attribute it to 2 different people, depending on where you are. Often people say that Gauss, Carl Friedrich Gauss, if you're taking physics that deals with electricity and magnetism, you see the name Gauss all over the place. The guy did lots of work in that field. So he lived from 1777 to 1858. Now, if you're from Eastern Europe or places near Russia or influenced by Russia, they will tell you that this thing was discovered by this other guy. Mikhail Ostrogravsky. 1801, 1862. So there you can think of them as the co-inventors of co-discoverers of this theorem. And in scientific world, who gets the credit often depends on who publishes first. It really doesn't depend on who discovers it first. If you discover it but you don't publish about it, then you often don't get a credit if someone else beats you to the publication. Just like Newton and Leibniz. Today there's still that controversy as to who invented calculus, and the right answer is that they both did a lot of work, but Newton published later than Leibniz. And so Leibniz in many respects get the first credit. Okay, so let's look at the physical reason behind why these 2 things are the same. So why is the triple integral of the divergence of the vector field inside some body equal to the flux integral of the vector field through the boundary surface? So think about it this way. If the vector field is representing a fluid flow, think of water or air flowing through some space, then we know from earlier that the divergence of the vector field measures the tendency of that fluid to either move toward a point or move away from a point. If the divergence is less than 0, then think at the point, then fluid will have a tendency to move toward that point. Think of the when you fill up a sink with water and you pull the plug, water should flow into the drain, right? So in that case, the divergence of that drain there would be less than 0. Things want to move toward it. And it would move away from a point if the divergence is positive. Okay, so then if you look at if you think about the meaning of the divergence that we're accumulating inside the body, and if you integrate it entirely over that body, then this quantity here will tell you overall, do things want to move out of that body or move into that body? Again, we're going to use fluid as an example because it's something that we're all familiar with. If fluid wants to leave the body or enter the solid. So you got to imagine this solid doesn't slow down the fluid flow. It's just an imaginary box, for example. Do things want to enter that, or do they want to leave that little box? If you imagine that we'll use the cube, it's a nice example here. So let's suppose that it turns out that the divergence is positive. So that means everything inside this box wants to get out of that box. So as time goes on, the fluid wants to leave like that, right? Also going to be exiting through the back surface. Well, the only way for fluid to leave is to go through each surface, all 6 of these surfaces. So that's what this is measuring. Remember, F dot ds is measuring the amount of fluid going through that surface. So if you look at the right surface here, for example, we're seeing fluid leaving. And how much left through this surface is measured by the double integral over S of F dot ds. Okay, that's what the flux integral is telling you, the rate of the fluid flow through that particular surface. So this is why we do a flux integral over every single surface around the body. You add all of them together, that will be equivalent to overall the volume change inside the box. Do things want to get in or do things want to get out? Okay, so that's a very quick physical interpretation of the statement of the theorem. Does that make sense? Yeah? Okay. And of course, you can actually prove this mathematically by using definitions of divergence and surface integral and work through the lengthy notation and all that stuff. It'll show you that both sides indeed are equal. But I like the physical interpretation a little bit better. Okay, let's try this on something. Let's have this vector field, xy square I plus yz squared j plus x squared zk and the solid we're talking about is bounded by a sphere of radius 3, centered at the origin, and the xy plane. So we're talking about the upper half of a sphere of radius 3 centered at the origin. If we're going to talk about the surface and do a flux integral, we have to know the orientation of the surface. And remember, usually, unless specified otherwise, you assume that for a closed surface, it's always oriented outward. We want the normal vector to point out of that surface. Here, we'll do the same thing. All right, so here's my hemisphere, the upper hemisphere. And we're going to draw a vector, a normal vector, just to remind us that's how it's oriented, outward. Okay? Let's first look at what we would have to do if we calculate the flux integral over this surface right here. If we're going to do this thing here, we need to break it into two surfaces. We have a surface right here. We'll call that S1. That's just the upper sphere. And then it is also bounded by this circle below, right? And then for each of these two surfaces, we need to parameterize it. So for S1, we need to have R of uv is equal to something. S2, R of uv is something else. Then Ru cross Rv for each. Then F dot ds, which by the way, remember, is the same as F dot Ru cross Rv du dv. And then with that, you also got to be careful that you want to make sure this is outward, because we want it to go outward, right? Okay, you've done this before, and you probably remember this takes quite a bit of work and time and patience to get through. So this is a pretty lengthy process. And before you knew the divergence theorem, that was the only choice you had. You just had to tough your way through this thing and get an answer for that. But now we know divergence theorem. We have a choice. instead of doing this tedious work here with the surface integral, we could do a triple integral of the divergence of f, right? And if the divergence of f turns out to be simple, then we're in really good shape. All right, so let's try that out. Okay, so let's first calculate the divergence. The vector field we're looking at is xy squared, yz squared, x squared, z. And the divergence of that is just the partial derivative with respect to x of the I component plus the partial derivative with respect to y of the j component plus partial derivative with respect to the z of the k component. And it's a scalar, right? It's a scalar. So that's another nice thing. We went from a vector integration here to a scalar integration. Okay, so what do we get? We get y squared. We get z squared in the middle, and then x squared up there. X squared plus y squared plus z squared. And the shape we're talking about is a very nice shape. It's just the upper hemisphere of a sphere of radius 3. And it makes perfect sense to describe this in spherical coordinates. Rho will be between 0 and 3, right? Phi is going to go between 0 and pi over 2. And theta is going to go between 0 and 2 pi. Theta is the angle on the xy plane. We went all the way around, so 2 pi. Phi is the up and down angle. Phi is 0 is straight up. Phi is pi over 2 is on the xy plane. So this gives us the upper half. And that's just the radius of the sphere. Also in spherical, do you remember what x squared plus y squared plus z squared turns into? Rho squared. Yeah. So that's really nice. We're integrating rho squared dv over 3 constant bounds. So this is a very nice example where the divergence theorem cuts the work that we have to do compared to the the surface integration. We save a lot of time and work and frustration. Okay, so let's integrate that. We get 0 to 2 pi, 0 to pi over 2, 0 to 3. Divergence of f is x squared plus y squared plus z squared, which is rho squared. And what's dv in spherical? Right, rho squared sine phi d rho d phi d theta. Okay? And what's left here is really pretty easy to do. We have rho to the 4th sine phi d rho d phi d theta. First round of integration is with respect to rho. Rho fourth becomes rho to the fifth over 5. Zero to 3 sine phi d theta. And 3 to the power of 5 is 243. 243 over 5 is a constant. Let's move it out. Next round of integration is with respect to phi. Okay? So we get negative cosine of phi 0 pi over 2 d theta. And this turns out to be a 1. And then we integrate 1, 0 to 2 pi, we get 2 pi. So it's 243 over 5 times 2 pi, which is 486 pi over 5. And that, of course, would be exactly the same thing you would get if you actually had gone through this process. Right? Parameterize the sphere, the circle at the bottom, find the normal vector, making sure they're pointing in the right direction, and then f dot ds twice, add them together, you will get the same thing. If you didn't make a mistake along the way. Okay, so it's not always going to be like this. Now, sometimes, depending on the shape, of course, sometimes the surface integral might be easier to do. In this particular case right here, because divergence turns out to be really nice in spherical, the divergence theorem makes the work very, very easy. But the important thing to remember, just like Stokes' theorem, is that you have a choice. This thing gives you a choice. It doesn't dictate which way you have to go, but it gives you a choice. Let's do another one. The vector field is x to the fourth I minus x cubed z squared j plus 4xy squared z k. And the shape we're talking about, the boundary surface of the shape we're talking about is the surface of the solid bounded by x squared plus y squared is equal to 1. Z is equal to x plus 10. And z is equal to 0. Okay, so we got our vector field. Again, imagine this is the fluid flowing around, and then we got some kind of shaping here. That doesn't change the flow, but we are somehow tracking the fluid going in or out of that surface. As usual, remember, unless specified otherwise, we assume that the surface will be oriented outward, which is the case here again. Assume the surface is oriented out. Okay, let's take a look at what kind of shape we're dealing with here. What shape is x squared plus y squared is equal to 1? Let's try that again. What shape is x squared plus y squared is equal to 1? Let's try that one more time. What shape is x squared plus y squared is equal to 1? Circle radius 1. Cylinder. Yeah, it's a cylinder. You're right. It is a circle radius 1. Each cross section is circle radius 1. But we're talking about 3-dimension, right? The missing variable means that it's unconstrained. It could go anywhere. So in the xy plane, we see circles radius 1. No z appears in here. So z can go infinitely high and infinitely low. We're going to cap below at z equal to 0. So let's start by sketching that. All right, so this thing will go up and down, right? It doesn't go down below 0. Goes up as high as this will allow us to go. What shape is this? Z is equal to x plus 10. What shape is this? A plane, good. Okay, tell me more about this plane. Okay. In words, how would you describe it? Good. And on the x and z plane, it's a line. Yeah. Okay. Right. So on the x and z plane, this is a line with a z-intercept of 10 and an x-intercept of negative 10. Right. Okay. So it's going to be a plane that's kind of it's going to slice through the z-axis at an angle. So that means it's going to slice through this and give us a cross-section of an ellipse. Okay, if you slice through a cylinder kind of diagonally, the cross-section is an ellipse. So that's the kind of ellipse we're seeing. It's inclined up towards us. Okay? All right, so if we're doing the surface integral route, how many different surfaces do we have to parameterize? 3, right. Okay, so you count, once with this kind of problem, you count the number of faces you're dealing with. If it's more than 1, consider going the divergence theorem route, right? Like 2 is not so bad, but 3, probably not the best way to do it. Just like with Stokes' theorem, you count how complicated your boundary curve is. You have to break it into 4 different parts, like a square. In that case, maybe you want to do a surface integral instead. Same thing here. How complicated is your surface? Okay, so now we've decided to go with the divergence route. Divergence theorem says that we want to do a triple integral over that thing, the divergence of f dv. Now the next potential difficulty here is how complicated divergence of f is. And can you integrate that? That's the next potential problem. So let's figure out what we got. Divergence of f, this will be 4x cubed minus nothing. There's no y here, so nothing out of here, plus 4xy squared. If I factor the 4x out, then I have 4x times the quantity of x squared plus y squared. Looking at this cylinder that's capped below at the xy plane and capped above, slanted in a slanted way by the plane, what do you think would be a good choice in terms of coordinate system that we want to consider? It's a cylinder, yeah? So what do you think? Cylindrical, huh? There we go. Cartesian might be okay. There's nothing wrong with Cartesian, but we're going to be integrating over a circle eventually. And once you look at a circle, if you started in Cartesian, integrating over a circle, you probably want to migrate over to cylindrical anyway. So again, let the shape determine how you approach these things. We're dealing with a cylinder. We want to work in cylindrical, more likely than not. Last example, we dealt with a sphere, and we want to do spherical, right? If this were a kind of a rectangular box, then Cartesian is a good system. Okay, anyway, cylindricals we want to work with here. The projection of that thing onto the xy plane is, of course, a circle of radius 1, right? So we're going to integrate over that. And then above here, we have that slanted plane this way. So r is between 0 and 1, obviously. Theta is between 0 and 2 pi, obviously. How about z? Bounded below by 0, right? What about above? X plus 10. But what is x plus 10 in this cylindrical world? Very good. R cosine theta plus 10. There we go. Okay? All right, so then the divergence theorem says to do this. We're going to integrate with respect to theta last, r next, and then z first. We have to do z first because z has the most complicated bound, right? Z has a bound that depends on r and theta. That means the integration with respect to z has to precede r and theta. It's going to have to happen first. The other two are both constant, so the order of the other two is not important. But z, this is crucial, z has to go first. And the divergence of f, let me write it here, divergence of f turned out to be 4x, x squared plus y squared. In Cartesian, that's not too bad, but in spherical, cylindrical, it's even better, because 4x is r cosine theta. And what's r x squared plus y squared? R squared, right? So that's 4r cubed cosine theta. And that's what we integrate. And what is dv in cylindrical? Right, we need an extra r, and then the order dz, dr, d theta. Okay, so that's not a bad integral to deal with. 0, 2 pi, 0, 1, 0 r cosine theta plus 10, 4r to the 4th cosine theta, dz, dr, d theta. the first round is with respect to z, and I don't see any z in here. That means I'm just going to get this thing here times z, and z turns into that. So this becomes 4r to the 4th cosine theta times r cosine theta plus 10 dr d theta. You have to do a little bit of trig integration, but that's really not that bad. Okay, so integration with respect to r, that's trivial. And then next round is theta. This is easy. This you have to use the identity, 1 plus cosine 2 theta over 2, right? So it's not really hard to do. But it's really boring, so I'm not going to do it. And it turns out to be 2 pi over 3 if you just carry through the relatively simple procedure here, which again is going to be exactly the same thing if you had gone this way. 3 different surfaces, parameterize them, Ru cross Rv for each one of them, integrate, 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 and add them together. Okay, so keep in mind that when you're working with something that involves divergence theorem, just start out by counting the surfaces you're dealing with. If it's 1, that's not so bad. If it's 2, that's not so bad. If it's 3, that's not so good. Consider going to the divergence route. Even though the 2 examples I've shown here turned out to be very easy once you've done the integration of divergence, that's not always the case. The important thing is the theorem gives you a choice. All right, the last thing we're going to do today is kind of a recap of the big theorems we've looked at. And I also want to point out the similarity between the very, very basic fundamental theorems we've seen before. So look at the common features here. The fundamental theorem of calculus relates the integral of the function to, well, one derivative later, right? Derivative of these guys, when you integrate them, shows back up. Notice that it's in the fundamental theorem of calculus, it doesn't really matter what happens in between the 2 endpoints. Only a and b truly matters at the end. We saw the same feature when we saw fundamental theorem for line integrals. When you integrate the gradient of f, we only need to calculate the potential function at the beginning and the end. The path of how you got there was irrelevant. Only the end points matter. So these two, this one is just a generalization of that. Only the end points matter. By the way, this table is in the book, so don't. And I also upload it with my notes, so don't worry about writing this stuff down. Green's theorem relates the. Notice the difference. Notice the similarity again. The difference is one integration, one dimension. Double, that's a 2 integration, 1. 1 integration, no integration. There's a one-dimensional difference. And they're relating the derivative of something on the 2 sides. And then instead of worrying about what's happening in the middle, we worry about the boundary. Just like here, only the end points, the boundary of that line, here we have a boundary of a surface. So as we progress down here, things keep becoming more and more generalized into higher and higher dimension. But notice the fundamental feature is still the same. We only care about what's on the boundary. Green's theorem is a special case of Stokes' theorem. And in Stokes, in Green's, D can only sit on the xy plane. But in Stokes, that surface can be curved, can be oriented just about any other way. And once again, we saw how we can relate the integration of the difference of one derivative. Think of curl as some kind of special derivative. So derivative of f and f itself here, and the difference is one dimension shown by the integration, number of integrations you do. Again, the middle doesn't matter, only the boundary matters. Just like here, only the end points matter. Finally, today we saw divergence theorem relates a body to the surface of that body. What's inside that body is completely irrelevant as far as the theorem goes. Only the surface matters. So this is just an extreme generalization of the fundamental theorem of calculus. The middle doesn't matter, only the endpoints matter. And of course, this thing can theoretically go on forever as we get higher and higher dimensions. We just can't draw them anymore. Once we go beyond here, we can't draw this thing anymore. But mathematically, we can deal with them exactly the same way. Okay, so this is a very, very nice table that I found in the book that kind of ties everything together. Right? It's really, some of these seem really, really, really strange, but fundamentally, they are all telling us the same thing, that what's happening in the middle doesn't matter, only the boundary matters. Okay, we'll end it there today. So look at the practice problems. Go through the first 18 for Monday, and then we'll do as many as we can on Monday, and then the next 18 for Wednesday, and so on. All right, have a good weekend. See you Monday. Talking about the whole sphere or just is this the atmosphere? Yeah, just pretend it's atmosphere. Okay. If we say it's oriented outward, that means every part of that surface has to have a normal vector that points out. Okay, so it doesn't matter if it's facing like the negative y or negative z, just as long as it's has to point away from the center of that body. And then that's generally positive. That's right. Okay. Unless